This experiment is conducted in a controlled industrial environment, specifically within a smelting yard and pit. Its purpose is to demonstrate the chemical stability of our compound under extreme thermal stress, preventing violent reactions such as explosions, phenomena commonly associated with the thermal decomposition of water exposed to temperatures above 1100 degrees Celsius. In this case, we will observe the direct interaction of molten slag at 1200 degrees Celsius, freshly poured from the furnace onto a slope, with our product, TCAS SGA, in order to assess its behavior under extreme thermal stress. We have termed this process inverse chemistry of extreme states, or ICES. As the slag is poured from the crucible, we observe maximum fluidity and the intense emission of gases typical of metal fusion processes. Under normal conditions, water subjected to such thermal ranges decomposes rapidly into oxygen and hydrogen, causing multiple explosions, molten slag ejections, and critical hazards for workers and facilities. This phenomenon is well documented in the metallurgical industry. Furthermore, the smelting of minerals at these temperatures releases corrosive gases such as hydrochloric acid, sulfuric acid, or hydrofluoric acid, depending on the elemental composition of the charge.
The entire experiment was carried out under strict safety protocols. Response teams were positioned behind protective barriers to mitigate any potential risks related to exothermic chain reactions. Although we are fully aware of the safety profile of our compound, all safety measures were taken in anticipation of any unforeseen events. The test was conducted with a headwind. The first droplets were applied in a controlled manner, avoiding initial saturation to enable a gradual reaction. The immediate absence of violent response confirms the inert nature of the product when in contact with incandescent slag. We see it flowing across the hot surface, initiating a remarkable process, ionization. This phenomenon, unusual at such extreme temperatures, occurs without generating vapor or explosions, even during the cooling process from 1200 degrees centigrade down to 400 degrees centigrade.
A stable pooling of the product is observed, which continues to progressively cool the molten slag. By forming a solidified layer, it enables freer and more controlled thermal dissipation. The absence of vapor during the critical phase has significant implications. There is no mass expansion, nor release of acid gases as byproducts, which dramatically reduces both environmental and structural risks. Most notably, our product resists thermal breakdown, challenging the traditional laws of aqueous thermodynamics. With the initial reaction stabilized, the operator intensifies the application. We observe the product flowing over the molten slag like a living layer. While there is boiling, there is no violent vaporization or explosive water decomposition. The thermal behavior of our compound is profoundly different from that of pure water. Although its base is 98% water, the remaining 2% fundamentally transforms its thermodynamic properties. As the molten mass drops below 400 degrees Celsius, light vapors begin to appear. This is expected, as ionization occurs only under extreme conditions. This is precisely where inverse chemistry is activated.
During the test, 4,000 liters of a 2% solution, that is, only 80 liters of active compound, were applied to 40 metric tons of slag contaminated with molten copper.
Most notably, our product resists thermal breakdown, challenging the traditional laws of aqueous thermodynamics.
In just 6 minutes, the temperature dropped from 1200 degrees Celsius to 200 degrees Celsius. In the subsequent 90 minutes, without further intervention, it continued cooling down to 100 degrees Celsius. This advancement did not exist within the classical paradigm. Water alone could never achieve this. Its molecular structure inevitably leads to violent decomposition under thermal stress. This experiment confirms that the concept of inverse chemistry of extreme states, developed by TCAS, represents a milestone in applied thermal engineering. It is not merely about cooling. It is about rethinking the control of matter-energy interaction under critical conditions. For example, can this technology cool an electric vehicle fire at 2,000 degrees Celsius? Yes, without steam and without toxic gases. Lava flow approaching a populated area? Yes, intervention is possible without fragmentation or gas toxicity. Our product, on the other hand, redefines boundaries. It allows us to control unstable thermal masses safely, cleanly, and efficiently. What we are presenting today is not yet found in textbooks, but it will be. We are TCAS, and this is our contribution to science, industry, and the planet.